In this example, we're going to apply u-substitution to help us find an antiderivative of sine of x times e raised to the cosine of x. Now, this looks like a pretty complicated integrand, but before we jump into it, I just want to remind us a few things about u-substitution. Now, when we apply u-substitution, I typically think about two specific things. When I think about u-substitution, I think about having products of functions in the integrand. In this case, we see a sine of x, we see that exponential or the e to the cosine of x also being there and multiplying against each other. The other aspect I think about is, well, the derivative of one piece of those functions or one of those functions entirely, it could cancel out something else that's sitting there. Now, I know that's a little bit loaded and there's some other details to iron out there, but basically that the derivative of something will help us cancel something else out. So in this case, let's go forward with u-substitution. Now, in these types of problems, we try to identify, well, what piece looks like the derivative of the other, or whose derivative is also sitting there in this integrand. And well, if we take a look at this cosine, we know that the derivative of cosine, well, that's equal to minus sine of x. And what's useful for us in this relation is, well, this sine of x, we sort of see a sine of x sitting there in front. So in this particular example, what I'm trying to think about is, well, I see that the derivative of cosine, when we multiply it on through sort of that u-substitution aspect, that's going to help us cancel that sine of x that's sitting there in front. So again, I'm thinking I'm going to make the cos of x equal to u. So let's see what happens when we go through all of the explicit mathematical details. All right, so if we call u cosine, we have u is equal to cosine of x. What that immediately means is, well, anywhere in that original integral where there's a cosine, we can go ahead and change that to a u. Now, the other aspect that's critically important in these u-substitution problems is, well, we have that dx that's sitting there from the original integral. We need to try and get that in terms of u, or in terms of du more specifically. So the way in which we do that, we visit our u-substitution and we differentiate it. So in this case, we have, when we take the derivative of what we called u with respect to x, we differentiate that cosine, we get a minus sine of x. And now, like I mentioned a moment ago, what we're really interested here is a relationship between a dx and a du, again, because we want to try and substitute in for dx to get something in terms of du. So if we just multiply both sides by a dx, we can get du is equal to minus sine of x times dx. And we can even do one better. We can solve for that dx all by itself. So if we solve for dx by itself, we'll divide both sides by a minus sine of x. And we get, I'll just draw this arrow, we get a du all over a minus sine of x is equal to a dx. And again, that's from dividing both sides by the minus sine of x. And that's exactly what we're going to go and substitute in for that dx down below. So I'm going to go ahead and erase that dx and just rewrite it with what we had from our substitution above, the dx for du, on that left-hand side. So we have a du all over a minus sine of x. And now what you might see is we have that sine of x sitting there in the front. We're dividing by a sine of x. We can cancel those two things out. So we're going to be able to cancel those out immediately. So the sine of x cancels that sine of x in the denominator. Now we have to be careful because we still have that minus sign, and that minus sign is really a minus 1, which we can carry out in front of the integral. So this integral becomes minus the integral of e to the u du, which looks a lot more friendly and a little bit easier for us to compute the antiderivative of that than that original integral. So the antiderivative of e to the u, and we're looking at what's left to do now, is, well, the antiderivative of e to the u, that is e to the u. And of course, since this is an indefinite integral, which means there aren't any integration bounds, we tack on a plus c. So we've basically found the antiderivative, but we're still one step to go. Namely that we have this antiderivative in terms of u, but the original variable was an x. So the last step for us to do is revisit our substitution, and anywhere there's a u in that antiderivative that we have, we substitute back in the x term. So in this case, we have a minus e to the cosine of x, and then just plus c. And that is our antiderivative in this problem. Now, one thing you might be wondering is, well, almost right off the bat, I looked up at this integral and said, you know what? I'm looking at that cosine and I'm thinking the cosine and its derivative, which is that minus sine of x, that's going to help us cancel out that piece out in front, that sine of x, that multiplying that exponential. Well, what if we didn't make that cosine u? What would happen if we let u equal sine of x? Because again, the derivative of sine is a cosine. Danger, we're not going to see that this is going to work out mechanically for us. And I just want to show us why. So what would have happened if we let u equal sine of x instead of u equaling cosine of x? The algebra really just simply isn't going to help us cancel anything out. But let's go through the details just to show you. Again, we can try things in math. Sometimes they work out, sometimes they might not work out. We can always try and see if we get stuck or reevaluate sort of what our decision-making process was. So again, in this case, I'm going to try and let sine of x equal u, which means if we let u equal sine of x, anywhere there is a sine of x in the original integral, we can swap in a u. So we have a u times an e to the cosine of x with that dx. And again, just like before, that dx we're going to re-express as a du by taking the derivative of our substitution. So again, our substitution now is u equals sine of x. So if we differentiate both sides with respect to x, well, the derivative of sine is cosine. And then what we're really after is how can we rewrite that dx in terms of du stuff? So we'll cross multiply that dx to the right-hand side. And then lastly, solve for that dx by itself. So dividing both sides by cosine of x. So we get dx is equal to, well, du over cosine of x. And that's going to be what we substitute in for the dx down below. So let's just go ahead and do that. So I'll rewrite this. So we have the u coming from the original sine of x that was sitting there. We have this e to the cosine of x. And now swapping in what dx is in terms of du, which is du all over cosine of x. At this stage, we've done nothing wrong or nothing illegal according to mathematics. However, that substitution we just tried isn't going to help us at all, because the issue for us now is, well, that cosine is sitting inside of that exponential, and the cosine that we're going to try to cancel it out with, well, that's outside of that exponential entirely. We're dividing by a cosine. The unfortunate aspect here is those cosines aren't going to cancel out. So the cosines in this case don't cancel out. And this is ultimately what the issue is if we tried to let u equal sine. We can try to let u equal sine in this case, and we just got to a point where, you know what, it just didn't work out. We weren't able to cancel out that cosine like we wanted to. In this case, we would go back and reevaluate that original integral and ask ourselves, well, was there anything else we could have let be u? And like we saw from the original way we did this, letting u equal cosine of x is actually the way to go.